Hello, everyone. My name is Kai. I'm from Hong Kong, UST. It's very pleasure to give a talk here. Actually, it's my first time to give a presentation. Can you hear me well?
Yes.
Okay. So actually, this is my first time to present in like Open Computing Conference. I usually give my talking in system networking communities. So I'm here to talk about our project towards a high performance AI computing platform for Hong Kong smart city applications. Actually, this is a very big project. I collaborate with many of my colleagues here in HKUST and in CUHK and in Polytech University in Hong Kong. So this project, we have two main parts, actually three main parts. So at the very bottom, we are building a AI computing platform, with GPUs, high performance networking, to form a large scale distributed AI computing system to support the smart city applications here in Hong Kong. So basically, in this part, we built a platform called TACC, the Turing AI Computing Cloud. So now this TACC has been open to HKUST CSE department. Many professors and students are using this platform for their AI and machine learning research. So the key feature in this platform is high performance. So basically, we use GPU connected by high-end networking protocols like IDMA. And our next feature to add on this platform is privacy preserving. We want to protect data privacy for our research, and also free to scale. So the goal of TACC is to support large-scale smart city application, smart city AI research. Okay, so this is at the bottom we have AI computing platform, and on top of it, we're many of my colleagues, collaborators in this project are building smart city applications. So first of all, we built a data set called CityNet. We call it CityNet. Hopefully, it's basically it's a CityNet describes a multi-model, multi-city dataset for smart city applications. So our goal, hopefully we want to create a smart city ImageNet, which can be used by researchers in smart urban computing and smart city. Okay, so this is a data set we're collecting, and we continuously looking for more valuable data to strengthen this data set. And with this data set, CityNet, so we are investigating different machine learning algorithms such as transfer learning, graph neural networks, spatial temporal machine learning, and also like recently we also look at the federated learning and so on. And based on these algorithms and data set, we hope to improve the smart city applications. Like we want to build a better taxi dispatching system, road planning, traffic scheduling, and so on and so forth. Okay, so that is a big picture. And this project, we actually have many colleagues, as I said. So we have high level speaking. So we have three main tasks. TACC is a high performance machine learning computing architecture. So I'm responsible for this part. Okay, and my colleagues who work on big data, is responsible for CityNet, and I also work on that CityNet. So based on TACC and CityNet, a lot of more colleagues are working on machine learning algorithms, smart city applications, urban computing applications. Okay, so that is outline. Today I'm going to talk about three aspects briefly. It's a big project, and these three parts, I select three pieces of the work from our project to share with you. Okay, and actually, some of our research is still ongoing. This is a 5-year project. We are just year 1. So first, I will talk about TACC, the Turing AI Computing Cloud, to support smart city applications here in Hong Kong. So for this part, I will talk about 2 aspects. One is, the one key feature for TACC is high performance, right? And why we call it high performance? We have a bunch of optimizations from system, from networking, and from just different aspects to optimize the performance of TACC. So I will talk about 2 parts. One is how we accelerate distributed DN training. So DN training is time consuming, as we know, right? Then how we accelerate the DN training from networking perspective. And then we briefly talk about how to speed up a graph neural network training. All right. So GN has been widely used and will be widely used in our project, and also in many urban computing and smart city applications, because algorithms applications in this domain can be modeled with graphs. Okay. And then we'll talk about CityNet, which is a multimodal data set for smart city applications. Hopefully, we build an ImageNet of urban computing, so that many researchers can use it. Okay. And finally, we'll talk about algorithms. All right, and we actually have many algorithm applications to develop. And in this talk, I will briefly talk about urban transfer learning, which is basically to address a common problem, which is data scarcity problem in urban computing. So from 2 perspectives, one is what if a city has limited temporal coverage data, right? What is the second one is a limited spatial coverage. So we'll talk about that later. So before we talk about that, we built a system in HKUST. So this graph shows our platform built here. Actually, this platform covers 10 years since I joined UST. Sorry, someone is locking the door. Just wait me for a minute. Okay, so let me continue. So basically, this testbed covers. I built this since I joined like 10 years ago, since I joined the HKUST, and it contains parts that we use for big data research, big data system research, and recently we built this a high-end TACC. So basically, this part is the right part is TACC, which we have GPU servers. We have 128 GPU servers, which is ITX 3090. Okay, so these 128 GPUs, in between, they are connected. So they are distributed in 12, actually 16. We have 16 GPU servers, and these 16 GPU servers are interconnected by high-end RDMA networking. So basically, this this platform is supporting quite a lot AI research here in our department. So now we come to the some technical details of the talk. First, I will talk about TACC, the Turing AI Computing Cloud. So talk about, we call it high performance because it's, we have put several system and networking optimizations to speed up the TACC. Firstly, we talk about DNN training, general DNN training. So actually, it's a focus on networking optimization for distributed DNN training. So as we know, so this picture shows a general DNN training procedure, right? So with the input, then we go through the forward propagation to compute a loss, right? So then with the loss, with the arrow, we go through the back propagation to compute the gradients, and then update the parameters in the neural network, and then we go through the next iteration. So this iteration go on and until we achieve a satisfactory arrow. Okay, so basically this DNN training procedure is very time consuming with complex model like ResNet 50, or now we have like much even more complex model like BERT or this NLP model and CV models. And also we have a huge amount of data like ImageNet. We have like 14 million. We have 14 million images, right? And with these complicated models and a huge amount of data, right, the training procedure is becoming more and more time consuming. For example, you train ResNet 50 with 8 V100 GPU, it costs 115 minutes, and BERT will cost, if you train BERT with 16 TPU, you cost 81 hours. Okay, so in current practice in production, so one way to speed up this training procedure is through data parallelism, right? So basically you divide your data into different workers, and each work has a model, a complete model. They train the model separate in parallel, right? And then they exchange the parameters, or the model parameters with a primary server. This is a primary server architecture, right? And then so with this data parallelism, right? So basically iteration by iteration, okay? So with this data parallelism, the hope is that we can, if we add more GPU servers to your training cluster, okay, then you can get more, speed up. Hopefully the speed up will be linear to the number of workers. Like you have 100 workers, you can speed up by 100 times. That's an ideal case. That's a hope. Okay, but in reality, we found that this is not the case typically. All right. So on the figure on the right, so you can see that at the top right, basically we can see that with the number of the x-axis is GPU servers and GPUs, and the y-axis speed up, as you can see, right? Where the number of GPU servers exceed 8 of 16, actually, if you increase the number of GPU servers, the performance or the speed up does not increase, it even decrease a little bit for some cases, right? And we can see performance degradation when the cross GPU server communication exists. So basically it's a nonlinear speed up, and we find the root cause is because of the network communication. So just during the distributed training, they also have you have computation on each individual GPU server. In between, you have a lot of network communications. So exchange between the workers and the parameter server, so that it will significantly affect the performance. Okay, you add more GPU server, you do not achieve expected performance speed up. Okay, so actually this is not a new problem, even for the machine learning community, right? So that's why people use optimizations such as specification or quantization to reduce the amount of track communication between the, for example, workers and the premise server. Okay, we also did an experiment to see whether this application level. So basically, we reduce the number of for example, gradients between the worker and the server. If we want to, use a specification or quantization, whether we can achieve some like performance speed up. All right. So this figure shows the compression ratio versus the network communication time. Here we call it FCT, flow completion time. It basically measures the communication time take during the distributed DNA training. Okay, and we have two metrics. One is average. That means that the average flow completion time. One is tail, which is the slowest one, which is slowest flow completion time. Basically, we found that the x-axis is the compression ratio. So that's amount of communication amount you reduced. Okay. So as we can see, right, if you reduce the amount of traffic by either specification or quantization, you can reduce the average flow completion time, the average communication time in the network. But the tail, you find that the tail is actually still there, remains very high. Even you compress the rate like 80%. Actually, in our experiment, we find even you have 95 or 90, more than 95% of traffic reduction, is still you can still see some very long tail latency. Okay, and actually in the training, it is the tail, the tail communication time decide the training performance. Okay, so that's a key part. You can reduce the average, but sometimes you cannot reduce the tail. Then which still be the significant bottleneck for training procedure. And this tail is due to the packet loss or retransmission. It's in for communication part. Okay, so then it means that we in our experiment show that even if we take this quantization or specification to compress traffic volume, it does not solve the problem. Okay, and then we investigate network optimization for this distributed DNA training, and in our optimization, actually we to design our algorithm, we made several key observations. Okay, and some of them very interesting. So the first one is here. This figure shows our first observation. Here, we found that the distributed DNA training procedure is a bounded loss tolerant, which means that if during the transmission, the certain packet drops in the network does not affect the model convergence. Okay, so as you can see, the y-axis is a convergence round. The x-axis is a data loss probability. You can see that with 2% packet loss during the training procedure, actually the convergence round does not increase at all, which means that it still converge to the same accuracy with the same communication like convergence round. Okay, so this is a very interesting observation. So with this observation, we come back to see our design opportunities. So currently, we as we know, many of you know that in internet, in network communication, we have two famous communication protocol. One is TCP, which is widely used by many applications, and one is UDP. Okay, so basically, if you use TCP, then it good side is that it can guarantee 100% reliability, which means every packet, every flow, every packet will be transmitted with full reliability. So because of this, it can maintain the good model quality because the deep training do not lose any gradient. Okay, and because it's 100% reliability, even if you have some packet loss, then you need to retransmit. That is provided by TCP communication protocol. And just because of this 100% reliability, it suffers from high communication overhead because it need to pay a lot of communication overhead if there are some packet losses happened, okay, which is a root cause for the long tail latency, as I mentioned in the previous slides. So that's a TCP. It's good model quality. It can guarantee good model quality, but the downside is it's very slow. The communication overhead is very large, okay? And on the other hand, UDP, it used, not widely used, but is also very famous communication protocol, transport protocol. So UDP, the feature of UDP is that it just transmit a packet, and without worrying about whether the packet is delivered or not. So according to this, it has a very low communication overhead because it does not worry about if my packet has been dropped. You need to retransmit. You don't do UDP. You don't do that. So because of this, the communication overhead is very low. Okay, it's very high efficient communication. Also, just because of this, it does not guarantee convergence, model convergence at all, because in the worst case, all the packet can be dropped, and then all the gradient can be dropped. So the model quality or the model accuracy will be significantly affected. So then we just find that. So for DRAM training procedure, actually it's the communication tolerates certain packet loss, which means some of the packet loss can be tolerated without affecting the model quality. So we leverage this property to design our DLCP protocol, which combines the benefit of both TCP and UDP while mitigate or avoiding their downsides. Okay, so that's an opportunity for us to design a high efficient communication protocol for distributed DRAM training procedure. Okay, so that's the first observation. In our second observation, basically we found that if you drop the packet, not all the packets are equal important, or that not all the gradient are the same. So basically, these figures show that for the first observation 2, figure 1, we find that if y-axis is convergence around the x-axis is loss probability. From this one, you can see that if you drop a large gradient, okay, then it will affect the convergence more serious. Okay, if you drop the small gradient, then actually it has less impact on the convergence. The right figure also shows that if you drop the front layer gradient, it has less impact. If you drop the back layer gradient, it has high impact. So I think this is because of pre-training, because in most cases, these models are pre-trained with some common data set, so that the front layer gradient or front layers, they're typically well trained. So if you drop some of their gradient, it does not affect the performance. Also, this is an interesting observation we made for DRAM training, so that we can leverage to optimize our TACC system. And the third observation is that the network traffic DN training is inter-packet independent. So this is this is different. This feature is also very interesting, because as you can imagine, in traditional most of traditional network applications, right? So the message is big, it's bigger than a packet. So typically, a message usually contains multiple packets, so that those packets has like ordering. Okay, if you transmit packet 1, 2, 3, and you receive the packet 3 first, that is not a good sign for network communication protocols. Okay, because those packets has ordering, so you are supposed to from the application you are supposed to receive the in order delivery of this packet. Okay, and so in DN training, so this is different, because in here you can view a gradient as a packet. That means a gradient is much smaller than a packet, which typically is 1.5K bytes. Okay, so in this case, that it means one packet has multiple gradients. That means one packet has multiple message, so that each packet are order independent, which means that you can transmit your packet freely across the multipath in your training cluster, so that you do not worry about like a packet out of order problem, which is a good feature we can leverage to design a more efficient TACC cluster. So based on these three key observations, we design the network optimization. For distributed DN training, we use a bounded loss tolerance to reduce the tail latency. We use the different gradients on different with different magnitude, value magnitude, and different layers to prioritize this gradient in network communication. And we use inter-packet ordering, inter-packet order independence to optimize to fully utilize the network multipath network resources in TACC cluster. Okay, this is a very brief idea about the whole picture. So basically, we have like per packet load balancing, because of the packet are interdependent, packet are order independent, so we can freely send this packet across multipath in our cluster. And then if the congestion happens, then our switch will perform priority queuing to drop the non-important gradient or non-important packet first. Okay, and then it will maintain good quality of the model. And finally, if the with the first two steps, we believe that there will be very little packet loss event happen. And even if the packet loss event happened, we are basically use bounded loss tolerance to solve this problem. Okay, so this ultimately come to our DLCP design, a deep learning domain specific deep learning network optimization protocol for distributed DN training. Okay, we implemented all these designs in our TACC. Okay, so next part I'll talk about GNN training. Okay, GNN training speed up. I think GNN training is getting a lot of attention and heavily used in machine learning enabled smart city research, right? Because it achieves state-of-the-art performance in applications such as the traffic prediction. I think many of you or some of you may use it. Okay, and GN structured data are natural representations of many real-world applications, including smart city applications, social networks, and so on. Okay, and GNN can capture structured information in graphs because the GNN computation process includes neighborhood aggregation operations, so it can learn from links between data samples. So this is also the reason behind the GNN's high performance in machine learning tasks. Okay, the figure here the figure in the bottom shows the process of GNN computation in a single node. Basically, it first aggregate neighbor nodes embeddings calculated in preceding GNN layer, and then apply the standard DNN operation, such as matrix multiplication, to get the final result. And however, you may know that training a GNN over billion age graphs is very time consuming and has scalability limitations, because a large number of neighboring nodes may be involved in the neighborhood aggregation operation, because each node need to learn from its, calculate the node calculation is based on the its neighbors, some of its neighbors, which is different from like some DNN model. Okay, so many existing GNN frameworks leverage data parallelism by partitioning the input graph and sending each partition to a worker. Well, each worker can simultaneously train the GNN over its assigned partition. Now, however, as we show in the figure on the right, so due to the neighbor aggregation operation, there are computation dependencies between graph partitions. So existing GNN framework suffer heavily from diminishing returns when scale out to a large number of computing nodes. So in our optimization, in our GNN training speed up, to solve the challenge I just mentioned, the scalability challenge, we propose a G3. It's a system for scalable and efficient GNN training, basically GNN training and graphs. We call it GNN training. So the top figure here shows the workflow of our G3 system. It has two steps: the partition step on the top and the execution step below it. So basically in the partition step, G3, our system, partitions the input graph for training. In the training step process, each worker loads the complete GNN model into GPU and train the model over the assigned partition. Okay, then in the execution step, we propose a spatial, we basically propose a parallelism strategy. We call it GNN hybrid parallelism, which basically enables both data parallelism and model parallelism. So more specifically, when a worker finish, its computation at one layer, the layer's output will not only be used in the next layer on the same worker, but also be transmitted to, peer-to-peer, okay, to other workers. If it, as long as these two workers, they have dependencies. And during that's a big idea, the general idea of G3. But in the design of G3, we have met two challenges. Okay. Basically, the first challenge is how to avoid stragglers in balancing workload distribution. So basically, if a worker takes more training work than others, such worker may become straggler and affect the overall training performance. In the GNN hybrid parallelism training procedure, when the degree of parallelism increases, the communication cost increased may not be evenly distributed according, across different partitions. Some existing systems use traditional graph partitioning algorithm to find a partition solution. But however, this graph partition algorithm is only suitable for a case where partition size is a good approximation of the workload. But in practice, not the case. With GNN hybrid parallelism, there are other factors, not only the size, partition size, there are other factors such as ages in a partition and the number of out-of-partition neighbors also affect the workload distribution. So we need a partition algorithm, all right? And this is the first challenge. So the second challenge is how to optimize the communication cost. So in GNN hybrid parallelism, workers communicate with each other and share intermediate results, which avoid computation duplication, but introduce a communication overhead in the meanwhile. So our solution, basically GNN hybrid parallelism, create opportunity to overlap computation and communication for both inter and intra-layer training workload. However, the communication, pattern, computing communication pattern, is derived from original graph, which can be interleaved and complex. So we need an efficient pipeline scheduling strategy to hide the communication behind computation, so that available computation and the network resources can be efficiently utilized. Okay, so actually we design, I think in our design, for the above two challenges, we have two solutions. The first solution, we basically to address the first challenge, we find that a traditional partition algorithm typically makes a partition decision with a minimum cut method. It only balances the number of nodes across partition, but not the workload. So we design our locality-aware graph partition algorithm, which introduces an iterative sweeping step on top of the traditional algorithm. Okay, so basically in each iteration, we first find two partitions that has the highest and the lowest number of remote nodes, and swap the nodes between these two partitions. We do that iteratively until the difference between the highest and the lowest number of coverage convert to below the certain threshold. And this graph show our effectiveness of our result. So our algorithm basically is able to achieve 3.9 times speed up compared to other partition algorithm. And to address the second challenge, our goal is to efficiently overlap communication and computation. We introduce a multi-level pipeline scheduling algorithm that pack per layer computation workload into groups, which we call the beans, and explore the CPU, GPU, and network overlapping opportunities with inter and intra-layer pipelines. So basically, in the middle of the figure in the middle, show our this one show our method. Okay. First of all, our bean packing algorithm allocate nodes into beans, and then GPU memory and used for GPU computation. And finally, the output will be transferred out from GPU. So in the middle, basically, we designed a scheduling algorithm which heuristically explores a large number of possible scheduling choices and estimate their cost using a learning-based estimator. And on the right, it shows our effectiveness our design. So we are able to find efficient pipeline scheduling decision that can speed up, deliver up to 3.6 performance speed up compared to the sequential execution. So this one summarize our work on GNN training. So basically, we designed G3 to tackle the scalability challenge in DN, distribute the GNN training with GNN hybrid parallelism in our TACC. And overall, G3 achieves up to 2.9 times throughput, okay, speed up compared to the state of the art work called DGL. That show the greatest, the greatest scalability where the cluster increases, okay. And so next, I will briefly talk about our, the second part of our data set. We call it a CityNet. So which is a multi-city, multi-model data set, which serves as a foundation for developing algorithms for smart city applications. So basically, currently we have constructed two versions of CityNet and developed a set of algorithms and application and the demo system upon it. So in the top left, okay, so top left, basically our CityNet version 1 contains data from a number of cities with multi-modalities. So CityNet 2, we focus on Hong Kong. We describe its urban phenomena from very aspects in detail. Okay, so basically the objective for CityNet version 1 is to discover different types of correlations among different subsets. Okay, for example, the knowledge transfer between different cities. This can enhance the digitalization of underdeveloped cities with experience and knowledge from well-developed cities. Second, it discovers the correlation among different modalities, for example, amounts and human mobilities. Okay, and in CityNet 2, which our dataset describes more details about Hong Kong, we have received a lot of help from Hong Kong government to build this dataset. Okay. However, the raw dataset, even though the raw dataset is still hard to use, for example, the traffic speed sensor dataset in our CityNet 2 may only cover a small portion of the region in Hong Kong. In Hong Kong, there are more than 6,000 roads, and we have like sensor dataset for only 500 of them. So this is the coverage problem. And also, we further assemble, individual dataset to construct a real dataset that describes the real-time urban environment. For example, we need to combine taxi dataset, bus dataset, ferry dataset, and subway dataset to formulate the urban transportation network of Hong Kong. Okay, and that's basically some description. With derived and assembled data in Hong Kong and transfer knowledge from other cities, we can further basically develop a set of smart city algorithms to best benefit the citizens here. We use technologies like transfer learning, IL, and so on. And we basically categorize the application into two classes. The prediction algorithm will use the status of a city, status of feature in the near future, and the decision algorithm will help citizens, enterprise, and the government to maximize the efficiency. So that's two parts. And in the following, I will introduce our CityNet as well as some applications according to these 4 points. So basically, in this picture, we show 3 dimensions to construct a urban dataset, including the time, the cities, and the services. So basically, we build the CityNet using raw data from several cities, including Hong Kong, like Shenzhen, Shanghai, and so on. In each city, basically our CityNet measures different services that the city provides for its citizens. So this includes information like city layout, weather, road, like traffic speed, and taxi demand, and so on. Okay, we can of course we can further use this information to construct high-level applications, which often forms a hierarchy. For example, as I show here, right, we can measure the traffic condition by combining the road condition and the transportation vehicle data. Right, we can further add the information about the human crowd mobilities to construct a comprehensive view of the entire transportation system. All right, and this system could be useful for analyze the phenomena and the transport network, since it contains information about different aspects like road stats, right, service providers and consumers, and so on. This picture shows introduced as a component of our CityNet version 1, which is our focus in the first year. It basically contains data from 7 cities. In each city, we partition the city map into small regions, and the data set in each city contains 8 sub data set or subset. So basically, among these 8 subsets, 3 of them describe the city status, including like weather, point of interest, POI, and connectivity. So basically the connectivity dataset is a region-wise connection on the road network. And the other 5 subsets are service data, including traffic speed on each road, taxi demand and supply in each region, human inflow and outflow in each region, all right? And basically the inflow measures the number of people moving into a region, the outflow measures the people moving out from a region. So for easy use of this dataset, we actually aligned all sub dataset in a spatial and temporal granularity so that it can be joint analyzed. We further conducted more than 200 benchmark experiments to measure the capability and the complexity of the dataset in a popular research field such as spatial temporal machine learning, reinforcement learning, and transfer learning. And in the following 2 pages, I will introduce 2 types of benchmark results briefly, which could review the correlation of the data CityNet among different cities and the different machine learning tasks. So basically, this picture, we use spatial temporal prediction experiment on 4 tasks to compare the performance between the single task model, okay, and a multitask model. And the objective here is to review, to show the relationships among different service data, including taxi and, basically taxi supply and demand, human inflow and outflow. So in this experiment, the single task model is the end-to-end prediction model by GNN with history of one type of service data as input and output the predict value of that type in the near future. The other one is a multitask model, which contains 4 types of service data as input and predict the 4 services themselves simultaneously. So according to this this figure, we find that on the similar model architecture, the multitask model can reduce the prediction error on average by 4%, which shows the effectiveness of the correlation among the tasks. And in this experiment, we use transfer learning across different cities to show the correlation between different cities in CityNet version 1. In transfer learning setting, so basically, as we know, there are 2 domains, which one is the source domain, the other is the target domain, right? And in our experiment, the source domain is y-axis. We have Shanghai and Beijing, okay, with abundant spatial temporal data. They are sufficient to train a complex and an accurate deep neural network, okay? And in the target domain, we have 3 cities, Shenzhen, Chongqing, and Chengdu. So the data set is insufficient and could support a very limited, only support a very limited model. So in our experiment, we first pre-train a complex model in the source domain and fine-tune it with a small amount of data in the target domain. And the results showed that the transfer learning, so compared to the supervised learning solution with small amount of data in the target domain, the transfer learning technique could reduce the prediction error by around like 8%, 85% on average. So basically, this graph shows the effectiveness of knowledge transfer according to city, in our CityNet applications. So CityNet version 2 is the next version where we're going to do this year or coming year. It will focus on Hong Kong and contain more details about transportation, human, and city environment. For example, in addition to taxi dataset, CityNet version 2 will also contain about the information about bus, MTR, ferry, road speed sensors, visual signals from road cameras, and so on. With this detailed information from different perspectives, we will develop more advanced algorithms and applications. So basically here, I only briefly mentioned 2 possible research directions. So the first one is to derive entire dataset with partially known information. So this is a very suitable for Hong Kong because there are more than, as I mentioned, there are more than 6,000 road segments in Hong Kong, but now we only have 500 of them So the data, like the traffic speed sensor data of 500 of them, then it will be challenged to infer the traffic speed on the road without sensors. Then how to do it? So this is one question we need to answer in the future. And the second problem is to assemble a complete like a view for an individual component. For example, using information from different means of transportation, like bus, subway, taxi. Can we suggest the best travel strategy for a citizen? Right, that's a question we need to answer. So finally, I just use a few minutes to describe. I think I am running out of time. I just use a couple of minutes to talk about the algorithms and applications we build on top of CityNet. Basically, we have many more. So we use CityNet. We actually develop like a traffic like taxi dispatching, right? Like bike sharing, some of these algorithms. But due to time limitation, I only talk about like urban transfer learning. Okay, so which is a common smart city algorithms. So basically, for application smart city, lacking of data, right, is a common practical issue, right? In general, there are two types of data limitation or data scarcity. The first one is urban data may lack, missing temporal coverage. For example, if you are a new bike sharing company, just entered a new city with just several days, right? The company only have several days of data available, right? So it does not have sufficient data in terms of the time, right? And second, urban data may also lack spatial coverage. Just as I mentioned in Hong Kong, right? So we have more than 6,000 road segment, but we only have like coverage that like sensor, deployed in 500 of them, right? This is another problem we need to address. So therefore, when we design algorithm for smart city applications, we have to solve the challenge of lacking data, right? One practical solution is transfer learning, as we know, right? Because with transfer learning, we can learn from source domain with abundant data and reuse the learned knowledge to the target domain. So in the following, I just introduced two pieces of work we did to tackle the lack of data issue in smart city applications. In the case one, we talk about we discuss the issue of limited temporal coverage. So suppose a ride sharing company has just entered Hong Kong for a few days. It only have several days of Hong Kong data and demand prediction for demand prediction, which may lead to inaccurate predictions. Right? In this case, intuitively, we may be able to transfer data knowledge from, say, Beijing. Okay, well, the company has a long service history by hoping that the ride sharing demand in Beijing shares some common knowledge with that in Hong Kong. Okay, but in practice, we found that there are still differences between cities. Right? For example, in terms of population and size, Beijing is much larger than Hong Kong. In these cases, or in this case, knowledge or model learned in Beijing may not be directly used in Hong Kong in a good way, right? So we face challenge of how to find city-wise invariant knowledge despite such differences. Okay, so our intuition to solve this problem is that despite the city-wide differences, there must be smaller units, okay, in both cities that are similar. For example, as shown in the picture, right? The financial street region in Beijing is similar to the central region in Hong Kong because they're both financial business region, and they are both very crowded and both within downtown area. So these regions share common transferable knowledge. Then the next question is how to find this region. So basically, to answer this question, our solution, we actually propose a system called a cross GDP, in which we find a similar region across city by learn domain adaptive multi-view region embedding. So by basically by projecting regions from both cities onto a unified feature distribution, we can easily find a similar region across cities. So to do so, we first use a multi-view data, including like POI, human mobility road layout to learn comprehensive road, basic region embeddings. Then we use domain adaptation technique to align region embeddings from both cities to a unified feature distribution. And finally, the region embeddings are used to compute the region similarity. So in our experiment, we show that for like a case that the Chicago-Boston city pair, the Boston University and the University of Chicago are projected to very similar, like similar vectors, which validate our intuition. So finally, so here is we introduce basically the experiment result with taxi and bicycle demand prediction through intercity transfer learning between New York, Boston, and Washington, D.C. Actually, the proposed method across GDP, which is indicated by the red bar, reduce a 7% prediction error in multiple source and target cities and various amount of target data. Okay, so finally, so after discussing the limited temporal coverage problem, we turn to talk about the problem with limited spatial coverage. So for example, as I mentioned, right? So we have 6,000 roads in Hong Kong, but 500 of them are deployed with speed sensors. In this case, we can only perform speed prediction in this 500 roads, which is a very small portion. Then we need to solve the problem how to leverage the speed data on 500 sensors to predict the speed on 6,000 roads. And intuitively, we can solve the problem by borrowing information from running taxis, right? The taxi run on a wide range of roads than these 500 roads with sensors. As they're wrong, we can approximate their speed from their positions. Thus, our intention is to bridge taxi speed with sensor speed to solve the problem. Okay, so so basically, we use of course we meet several challenges when we bridge in taxi speed with a sensor, due to several aspects. Okay, so the first one is despite the wide coverage of taxi, not all the roads are occupied with taxi at all times, right? As a result, there may be many missing values in the taxi speed. Second is the taxi speed derived by GPS logs will be much lower than those recorded by sensors. The difference may be caused by for example, the straight line assumption of taxi. Maybe taxi just do not go through straight line, right? Or events such as pickups, right? So the distribution difference is shown in the figure. We can see the difference there. And finally, the taxi speed are uncertain, as different drivers may predict different speed even on the same road at the same time. Okay, we also see this difference. So basically, to solve this challenge, we design method containing 3 techniques. First, we use community information to fill the missing value and use inductive graph learning to generalize the model to missing values. Second, we learn a translation module to translate taxi speed to sensor speed with aligned distributions. And finally, we use a Bayesian learning objective with both mean and variance